hear a little bit about machine learning and material science today from Dr. Anubhav Jain. He got his undergraduate degree at Cornell in 2006 in applied physics, and he got his PhD at MIT in 2011 under Gerbrand Sater, who's now a professor in our department in material science and engineering. He's a research scientist at Lawrence Berkeley National Lab up at the Hill, and he's one of the PIs in the materials project. And he heads the Hacking Materials Group, and we have a member of the Hacking Materials Group here, Alex Hung. And you're going to hear about their work on some of the open source software libraries that they've been developing for doing machine learning on materials data. And it's a really exciting part of our field right now. It's developing very quickly, and tons of new stuff is coming up every day. So we're really pleased to have Anubhav here to talk about this cutting edge part of materials science.
Great. So thanks very much, John, for that introduction. Before I begin, I want to say that all the slides are already online on this website, so you don't have to try to eat pizza and write down citations at the same time. So just take the slides from there. I wanted to begin by saying why I got into materials and why I think this idea of trying to accelerate materials design is important. And the reason I got into materials is because I started to feel that materials and their properties really determine what is technologically possible. So if you look at two things, electric vehicles and solar cells and solar modules, these were actually thought of and dreamed up a really long time ago. So electric vehicles existed, as many of you know, back in 1910. And there were thoughts about solar power kind of taking over the world back in the 1950s. So these ideas have really existed for a very long time. But what's really happened in the last couple of decades is that the materials advancements have reached the point where these can now be large scale and make an impact on society. So in terms of electric cars, it wasn't the wheels that got better or the headlights. It was really the battery and coming up with new battery chemistries that made the difference. Similarly, in solar, it wasn't some new idea really. It was just materials manufacturing, materials engineering, understanding materials defects. These are the things that really made the difference in these being just ideas for many decades to actually having societal impact. The issue, though, is that as these examples kind of demonstrate, it can take a really long time to develop a new materials technology and to bring these ideas into society. And if you look at why that is, it's because a lot of the ways people discover and design new materials is still fairly traditional for the most part. So here's a quote from a paper. And this is a really famous battery research group, Duran Arbach's group. And they're looking at the next generation of batteries past lithium. So these are magnesium batteries that would carry 2 charges per ion. And they actually discovered the first cathode material, the Chevrel material, that actually works for these new types of batteries. And in one of their papers, they described how did they find this material. And what they wrote is it resulted from a lot of unsuccessful experiments of magnesium ions insertion into things that were already known to work well for lithium. And they also did a lot of literature analysis as to what sorts of materials might actually let 2+ ions diffuse through the material. So you can imagine that doing a lot of unsuccessful experiments, relying only on literature search, can be something that is a little bit unpredictable and could have room for improvement in terms of being able to accelerate materials design. So this talk is really about a few different ideas of things that we can do moving forward in order to kind of move beyond this process and add new tools to the repertoire of experimental groups. Okay, so here's kind of an outline of the talk. The first part of the talk will really be about density functional theory and automating it on large supercomputing centers. The second part, as John had mentioned, is about software. So a lot of software libraries that we're developing to help researchers also do the same things that we're doing and also to do some machine learning type work. And then finally, I'll describe a project that we started fairly recently about text mining and natural language processing of journal articles in order to do materials design. Okay, so I'll start with this first topic, which is high throughput density functional theory. So as probably most of you are aware, density functional theory is a computational modeling technique that can tell you the properties of materials from first principles. So in the 1920s, the Schrödinger equation for quantum mechanics basically told you how electrons interact to form systems and form various electronic states. And pretty much all of chemistry was embedded within that Schrödinger equation. The problem was that it's basically too complicated to solve for any realistic material system. So in the 1960s, Walter Kahn and others basically developed this density functional theory technique that reframes this interacting electron problem into a much less complex problem that depends only on the charge density. And what this did is it actually made it possible to solve approximations to the Schrodinger equation using computational techniques, and in a way that doesn't really sacrifice too much of the accuracy for a lot of practical materials. So this ended up winning a Nobel Prize. If you're unfamiliar with density functional theory, in practice, the way that it works is that you define your material system. So these are atoms in a repeating cell with periodic boundary conditions. And you can have different atoms at different locations that describe the material that you're interested in. And then you apply some computational power to actually solve these DFT equations. And you get back fundamental properties of this material. So this is the electronic band structure of the material. And then you can do further processing on these fundamental properties to kind of get technological properties of your material. So in this case, you can take the band structure and apply some transformations to get an optical absorption spectrum. So this is what wavelengths of light does this material absorb compared to the solar spectrum. And you can use that to help screen for solar absorbers. There are many other types of things you could do with DFT. So for example, if you were to take the energy of your structure and compare that to the energy with atoms removed or replaced, you could get defect energies. You can calculate diffusion barriers of ions migrating, which is relevant for batteries and other things. You can also get things like phonon modes, elastic tensors. So there's a whole bunch of things that you could compute with this technique. People are often interested in how accurate this technique is. And the answer is that it always really depends on what are you looking at and also which flavor of DFT you're using. So here's a few different examples. If you're computing battery voltages, these are typically on the order of 3 or 4 volts. And this is the error that you get with DFT for different types of materials. If you use just a standard DFT approximation called GGA, you can get pretty big errors. I mean, these are like 20% errors, for example. But if you use more advanced DFT techniques, so this is the plus U method or hybrid functionals, you can actually get fairly small errors on the order of experimental errors sometimes in terms of predicting battery voltages. You can also predict band gaps of materials, and this is one of the areas where DFT, in particular the standard approximations, are known to be really bad in that they really underestimate experimental band gaps. So the predicted DFT gap is much smaller than the experimental gap. But there are techniques, including hybrid techniques and this other one, delta sol, that can get you much closer if you think to apply that technique. And then finally, other properties. This is the bulk modulus of a material. You can see that calculations and experiments are pretty close, pretty much always within 15%, even with standard techniques. So for every single application that you're looking at, you really have to think about, what's the flavor of DFT that I want to use? Can I just use standard techniques, or should I use something more complicated? And then again, many of you are probably already familiar with this, but DFT is also limited in length and time scale. So for short length scales on the order of, let's say, 1,000 atoms in a repeating cell, and time scales on the order of, let's say, femtoseconds or maybe picoseconds, you can do ab initio. But if you want longer time scales or longer length scales, you really have to use other types of computational modeling techniques. So this is all pretty well established since the 1960s onwards. One thing that a lot of us here at Berkeley, including myself and Christine Pearson and Garrett Sater, have really did over the last 10 years is this idea of high throughput density functional theory. And the idea there is that instead of just running DFT on one material at a time, we actually automate the procedure and run it on supercomputing centers so that we can do thousands or hundreds of thousands and sometimes even millions of materials. And what this really requires, first of all, is to develop a software infrastructure where we can make complex computational workflows where we do sequences of DFT calculations that depend on one another and use the results from other ones in complex ways, and be able to store millions of these workflows and execute them on these supercomputing centers. There's one called NERSC at Lawrence Berkeley Lab, which is about 100,000 different desktop machines. So imagine everybody here had 500 computers or something running all the time. That would be like the size of NERSC. So being able to run these calculations on these large supercomputing centers allows us to maybe screen lots of different materials with this density functional theory technique. And this is something that was listed in Scientific American as kind of a world-changing idea. many of you probably use this technique already, that you're in one of these groups, and like Alex is in one of these groups and are used to this idea of high throughput DFT. I want to maybe mention why it wasn't always obvious to do this automation of density functional theory. One objection I got back in like 2008 was this idea that density functional theory is too computationally expensive. So one calculation might be 100 CPU hours, so on your laptop, let's say a couple of days, or it might be 1,000 CPU hours, so maybe a week on your laptop. And so one critic would say, you know, it's too expensive to ever apply this technique to an entire database of compounds that's maybe 100,000 compounds. But what happened was that DFT implementations got faster over the last 10 years, computers got much faster, and people didn't really extrapolate where computing would be in 5 to 10 years. So for example, the Department of Energy has this InSight program for large computing grants. And in 2003, it awarded 5 million CPU hours in total. In 2018, it awarded 6 billion CPU hours, so basically 1,000 times increase. And it's really hard to visualize or really get a sense of this. I mean, imagine you had a research group with one person in it today, and then in 10 years it had 1,000 people in it, right? It's really hard to visualize how fast things can change when that happens, and what else is possible. Another sort of criticism was that managing all these calculations would be hard. And in fact, even Gerd Sater, who was my advisor and really thought of a lot of these high throughput ideas, when I first joined his group, he said, if you can build a system that just keeps track of where all our calculations are, I would already be impressed, right? And you know, nowadays, there's a lot of people are familiar with databases and data management, and it's a whole technique. But you know, back in 2005, 2006, I mean, even Facebook looked like this, and you couldn't even like upload pictures. You just had like a really rudimentary database of information. So back then, it wasn't really clear that you could build this sort of a system. And the last criticism, I think this one still sometimes appears, is that in order to run these calculations, you really need a trained researcher to set the correct parameters, monitor the job, and fix errors. And what it turns out is that actually standard density functional theory calculations are pretty routine, and you can automate them. And in my opinion, actually, it's even better that to do it automatically rather than to have a trained researcher, because if this is indeed an ab initio technique that doesn't require tunable parameters that you can't fudge the answer of, there should really be an automatic way to do it and not a way that requires a researcher to really tune it. And other things that people thought might be difficult to automate can actually be automated even better than maybe a researcher can do it. Although there's still a lot of other types of calculations like defects and GW calculations that still require trained researchers to do it. Okay, to give you an idea of this high throughput technique, here are a bunch of studies that have been done in the past that do high throughput screening to find materials. So you can see that this high throughput DFT technique has been used to find many different types of technological applications. And typically people will do calculations on like 10,000 to 50,000 different compounds and find only a few, only like a handful of those tens of thousands that actually meet the computational criteria for being good at this application. So the hit rate is actually pretty small, like usually 1 in 1,000 or so, which explains why it's so hard to find new materials for an application. And most of these hits are actually just computational hits too. Getting something to work in experiments is even much, much harder. And only a few, as of this point, only a few of the studies that are mentioned with the star had actually experimentally verified the candidates as well. So it is a pretty hard problem. Here's some examples of work that I've been involved with where we actually were able to come up with new materials in the computer first and then actually have experiments verify that it had the characteristics, at least some of the characteristics that we predicted in the computer. So earlier on, I worked with trying to find battery cathodes, and this was a new class of sodium, well, initially sodium-based that we substituted with lithium cathodes that actually showed pretty good performance as batteries. This is something that, this basically shows electrochemical discharge and charge, and as is, this material is not too impressive. We thought we could get 2 electrons of this material, which would basically double the length of this curve, in which case it would have been really interesting, but we could never actually get that second electron. We did some screening for carbon capture compounds as well. And then I'll talk more in detail about this last project, which is the screen for thermoelectric compounds. We basically wrote a review paper where we went through many different examples from many different research groups, where now they were actually able to find materials through this high throughput screening technique and have experiments verify them. So it's a pretty exciting time in that we are actually at the point now where in a computer you can screen for new materials and have those things actually appear in real life, and that's something that didn't really exist before. Okay, so let me describe our project to search for new thermoelectric materials, just so you get like a taste of how some of this technique works. So if you're unfamiliar with thermoelectrics, these are materials that will generate a voltage based on a thermal gradient. So if one end of the material is hot and the other end of it is cold, you can think of it as electrons diffusing from the hot to the cold side until this builds up an electric field that resists further motion. And these thermoelectric materials can actually generate electricity from a thermal gradient. They're used in spacecraft, and they're also companies that are trying to make really big systems that will take industrial waste heat, take the hot gas out from some power plant, put it into this like tractor trailer thing, which is a bed of thermoelectrics inside, and create an electricity power generator. So this is one of those examples where people have dreams of things that might exist, turning waste heat to electricity, but the materials are not necessarily there yet. So in order to get a really good thermoelectric material, the thing that people typically focus on is this figure of merit, sometimes referred to as ZT. And it's easy to remember what a good ZT is, because basically 1 is good, and more than 1 is like really good. Commercial ones are around 1, for example. And there's many ingredients to getting a high ZT. You need a high Seebeck coefficient, which tells you how much voltage you get per thermal difference. You need a high electrical conductivity, so you can actually get current to flow through this thing. And these two things together is called a power factor. And you need a low thermal conductivity, because that actually maintains your thermal gradient across the material. And the problem is that it's actually really difficult, because these properties all work against one another in typical materials. So as you increase one, you usually decrease the other, or you increase this one, you increase this one too, and so you end up with the same ZT. So it's really hard to do this using intuition alone. Here's one example of why that is. So here's a schematic of an electronic band structure. And if you have a really heavy band like this, you end up with a large density of states, which gives you a higher Seebeck coefficient, and it also gives you more carriers, which is good. But now you also have a large effective mass, so you have really bad mobility and bad electrical conductivity. If you have a light band, then you have a small effective mass, so you have good electron mobility. But you have a small density of states, so now you have lower Seebeck and also fewer carriers into your band. But if you have multiple bands off symmetry, you can actually get a large density of states, because you'll get multiple bands contributing to your density of states, but you'll still maintain your small effective band mass. So that's the ideal situation, but now these are difficult to design. Nobody knows how do you get a material with this characteristic. There's no theory that tells you, hey, use these atoms or use this sort of structure. So people thought actually as early as 2003 that, because it's so hard to find these things experimentally, maybe you could use computers almost like a virtual test tube as a way to screen new thermoelectric materials. And that way theory can kind of be a dance partner for the experiments in order to help find these thermoelectric materials. One problem, though, is that the screening of thermoelectrics with computations is not trivial. And the properties of thermoelectrics that you want to model are actually difficult to do in high throughput accurately. So for example, here's that ZT again, and here's the numerator of it called the power factor. And using the standard high throughput technique, which is a constant relaxation time approximation, this is kind of the correlation you get between experimental and calculated power factors. And you can see that, okay, it's kind of okay here, but it's definitely not great over here, and there's like problems here as well. So it's not really at the level that you would want. And then the thermal conductivity too, there's still like quite a bit of scatter in terms of the computations versus the experiments. So certainly in order to actually do this high throughput screening of thermoelectrics, it would be better to have improved theory. And that improved theory does exist, but they typically are not automatic or too computationally expensive to run on lots of different compounds. So one of the things we're doing in our group is actually trying to develop better computational models that will actually predict these sorts of mobility properties of electrons, for example, using much fewer computations than is typically needed for these expensive techniques. So here's one where the dots, for example, is the electron mobility as a function of temperature. And this AMSET model is the one that we're developing. And this Boltz trap model is kind of what's typically used for high throughput density functional theory. And you can see that there's certainly improvement. But there's other materials where this doesn't work out quite as well that we're trying to solve. So in the meantime, what we've done is we actually did do high throughput density functional theory on about 60,000 different materials, and we computed a lot of these electron transport properties to get the numerator of this ZT factor. So this is a plot where every single point is one material that we've computed. And this is the electrical conductivity with this constant relaxation time approximation. This is the Seebeck coefficient. And this is kind of a plot of the relationship between the two. And you can again see these sorts of trade-offs where as one gets big, the other one gets small, so it's really hard to get both of them at the same time. What we did, though, is we looked through all these different data points and tried to come up with a few that looked interesting and that weren't studied before for thermoelectric materials. One of them is this thulium silver telluride material. Our experimental collaborators, despite the presence of thulium, were actually pretty interested in this material because they had worked with some silver tellurides before. And what we found in our computations is that the band structures of these materials had this characteristic. So these are two different phases at two different temperatures of thulium silver telluride. But the band structures had this characteristic of having these multiple bands kind of aligning at different K points that would give you the high density of states, but also give you a low effective mass. So go ahead. No, so what we typically do is we start with crystal structure databases that have mostly known materials, like inorganic crystal structure database, and start with that. But then we'll do substitutions and things on them as well. So this is a known material that never was tested for thermoelectrics, for example. Okay, so we found that this could have a really, really high power factor, about 8 milliwatts per millikelvin squared, if you could get about 10 to the 20th per centimeter cube charge carriers and dope this material really well. So we did some experiments on this based on the computational studies. We got a ZT of about 0.35, so that's not great. Remember, we're kind of aiming for 1. And we got really low thermal conductivity of about 0.25 watts per meters Kelvin. This is really, really low for a solid state bulk material. But the big problem was that we couldn't dope it to that 10 to the 20th that we needed. We later did defect calculations and found that the thulium on the silver side is likely your p-type killer and is preventing you from getting really 10 to the 20th carriers on it. So not being able to predict how well you could dope this material was probably the big limitation here. Based on this, we did some more substitutions. We found this yttrium copper telluride material. And this one was less promising, especially after we added spin-orbit coupling, which removed some of the degeneracy of the bands. But we still found that we could get pretty decent, maybe a ZT of around 1 of this material in the computations. In the experiments, we were able to get basically the carrier concentrations we want. We got a ZT of about 0.75, which is pretty close to what we predicted, but we couldn't really get it further than that, even with further optimization. So we're still kind of hunting for new materials that have ZT greater than 1. I would say our lessons so far is that we still need better methods to actually be accurate in terms of predicting power factors and thermal conductivity without increasing the computational costs. But maybe most importantly, we found that a lot of materials we predict are really good in theory if you could dope them, but we're having trouble actually predicting can you dope them or not, because these doping calculations are not something that you can do in high throughput for the most part right now. So definitely more ideas are needed. There's other researchers working on this as well. And we're also working on using other techniques like text mining to suggest thermoelectrics, which I'll talk about later in the talk. Okay, so that gives you some flavor of using high throughput density functional theory to try and find new materials. We've also been writing a lot of software to try and accelerate these searches for materials, both to try to make these high throughput searches more accessible to others, as well as to do machine learning in material science. So I'll first start talking about Atomate, which is our code to automate these calculations. So since this high throughput thing has come together, here at Berkeley, we've actually generated many, many different data sets. So I already talked about this one about thermoelectrics with 50,000 materials in it, now about 60,000. But we've also computed lots of full elastic tensors of materials, about 7,500. I think in experiments, about 500 full elastic tensors are known, and about 1,000 piezoelectric tensors, and many more band structures and other sorts of computations. So certainly here at Berkeley, we can generate lots and lots of different materials data sets. What we wanted to do, though, is to make it easy for other researchers to generate comparable data sets on their own. So anyone in the world can generate whatever data sets they want for whatever purpose they need. And we thought about the problem and we said, well, how do you currently perform DFT calculations? What's the way that people typically do it? So first you have a question like, what is the elastic tensor of gallium arsenide with a certain DFT approximation like GGA PBE? And then what you need to do before you actually get that result back is a whole bunch of really small and annoying steps. Like first you have to write the structure coordinates file. You have to write all the input files to your DFT code like VASP. You have to copy all those files to your supercomputer, submit them to a queue, deal with supercomputers being down and stuff, monitor the job, fix the errors, and repeat all this process for every single one of the things that you want to get the calculation for. And most of your time is not spent here or even thinking here. Most of your time is kind of spent in this section of it. So we thought, well, what should it be? Like, what would be a better way? Like, what should go in this box once you have a question of, a calculation that you want to do? And ideally, it could just be like a checklist of saying, okay, I have my crystal structure of gallium arsenide. I kind of want the band structure. I want the elastic tensor. I want the thermal expansion coefficient. And then I just kind of click go and come back later, and I get back the results. So that's kind of the idea of what we want, right? And then if you want to do something even more complicated, like starting with all the binary oxide compounds, so not just one compound, replacing oxygen with sulfur and running many, many different properties and getting a database of results that we can query and explore, that should also be possible and be able to scale to millions of calculations. So you could do one calculation, you could do a million, and this would support everything. So our goal with writing Atomate was to try and bring some of these ideas like forward and actually make progress towards making some of this stuff a reality. And at its heart, what Atomate is it's a way to start with really high-level specifications of what you want. Like, I want an elastic tensor of a material. And it's code that turns those high-level specifications into really specific workflows of calculations. And here, for example, is a diagram of how to calculate an elastic tensor given a structure. It involves relaxing the structure, deforming the structure, doing many, many deformations in parallel, fitting the elastic tensor, performing a whole bunch of checks to make sure everything makes sense, and if they don't, to rerun with even stricter parameters, like numerical parameters, putting the results in a database, and then pushing that off to a website. So a really simple high-level instruction might correspond to a really complicated workflow, and typically you would have to conduct this workflow yourself, but we want to write software that automates this. So in Atomate, we've actually encoded the workflows for many, many different types of materials calculations, including band structures, spin-orbit coupling, elastic tensors, piezoelectric tensors, thermal expansion, ferroelectric properties that have been contributed by many different people. And so now you can actually just say that for one material or for 1,000 materials, let me just check off these properties, and these are the ones that I want to get. And then you submit it to the supercomputer, and you come back, and you actually get a database with all of the results. To dig into the details a little bit about how this Atomate software works, you need to provide Atomate with a structure or a bunch of structures if you're doing many calculations. And the big thing that Atomate does is it actually turns those structures into specific computing workflows. So these are series of density functional theory calculations that depend on one another and pass data, for example, between one another. And we store every single one of these workflows that you want to run. You might run multiple on the same material or multiple materials into a database. And this database can contain millions of calculation workflows. In fact, our database does contain millions of calculation workflows. And then we wrote a software called Fireworks, which actually can take this database of workflows and execute them on supercomputing centers or even on your laptop if you'd like, and manage all these calculations and the state of all these calculations. And then when the workflows are finished, it actually puts all the results both in a file system like you'd be used to, as well as a database that you can query. So this entire workflow diagram is implemented through Atomate, as well as some other codes that we wrote. And the whole goal is to take all these simulation workflows. So for example, Tess, who's here at Berkeley and talking next week, knows how to run ferroelectric calculations, and she contributed a ferroelectric workflow to Atomate. Matt did a lot of magnetic workflows. John, I don't know what you did.
I did the XAS smoothing code.
Okay. So basically, most of these people don't know how to run every single one of these workflows that's in Animate. But the idea then is that we can take all this knowledge of, John knows exactly how to run XOPS workflows, and then give that power to every single researcher. So anyone can run any of the workflows that any of the other people in this group know how to run. And really give you kind of increased power and productivity in doing these calculations. So this software is used by many research groups. It also powers this materials project website that's run here at Berkeley. I think Christine Pearson gave a talk about this website in the last session, so I won't talk about it. But in case you're not familiar, this is an online database with about 85,000 materials and all these properties that we've computed of those materials. It has about 60,000 registered users, and it's free. So if you're looking for materials property data and you haven't found materials project yet, I encourage you to check that out. So if you're interested in this Animate software and you want to do these high throughput DFT calculations, and it's not just theorists that are interested. I mean, there's a lot of experimental groups that want to dabble in theory, run a few calculations, but not necessarily worry about, what's all the flags that I need to set. There's a few different ways to get started. We have a paper that kind of just gives a general overview of what this software is and what it does. The documentation will actually run you through installing it and how to get started running some test workflows and doing some analysis. And then crucially, we also have this support list where you can ask questions and get back answers relatively quickly. So if you do run into problems with installation or something, you can send a question there. I think somebody in this audience has one outstanding question that I need to answer. Is that right? No? No? Okay. There was one question about, that I need to answer, but okay. So that's Animate. The next software that we're developing is MapMiner. And this is a software that we're bringing forward to help machine learning in material science. So normally theory will start with a small number of principles and keep extending those principles to get more and more cases. So it's kind of like growing the theory. Data mining is more like starting with a very large space of possible models and just removing the ones that are inconsistent with your data set. So you need certainly very large data sets to be able to distinguish between these possible models. The big promise, though, of data mining is that whereas, for example, density functional theory might take days to run for a single material, machine learning could give you a prediction in a second, for example. So whereas you might be able to do 10,000 materials with density functional theory, you could do 10 million materials with machine learning. And so that's really very powerful if we can actually get really accurate machine learning models. In order to actually do machine learning on materials, you need a data set, right? And crucially, you need a bunch of input data and output data, and the machine learning model will try to relate these two things together. And the two big problems for material science has typically been, how do we first of all get enough output data in order to train a machine learning model? Materials data sets tend to be pretty small, like a few hundred data points, whereas people in machine learning might be used to data sets with 10 million data points. So how do we actually get enough output data to be able to train a machine learning model? The other big problem is that, so material science quantities are things like chemical compositions or crystal structures, which are positions of atoms in space. But machine learning doesn't understand what a chemical composition is. It just knows numbers, and it knows how to relate numbers to other numbers. So you need to turn these chemical quantities, like compositions or crystal structures, into some physically relevant numbers that describe what that composition is or what that crystal structure is. That way, the machine learning model can take those characteristics of your composition or structure and relate that to the output. So for example, one of these descriptors might be the average electronegativity of the elements that are in your composition. Or another one of these things might be the difference between the highest radius and the lowest radius of the atoms in your composition. But the more physically relevant you can make this, the better, the easier job the machine learning will have in terms of getting good relationships between them. Some of you that are familiar with machine learning might say, well, to solve this problem, just use an autoencoder. So autoencoders will turn high-dimensional complex quantities into descriptors, a smaller number of descriptors that typically work well with machine learning. And there's actually a lot of problems with doing that. And fortunately, Tess will talk next week about this exact topic. So if you're interested in using autoencoders to solve this problem, I think she'll kind of outline what some of the issues are with that. Until then, though, people have come up with their own kind of hand-tuned ways to turn these chemical quantities into descriptors. So what we do in MapMiner is we try to make this whole process of doing machine learning on materials much simpler and kind of more of a community effort. And there's a few different aspects of MapMiner. The first thing it allows you to do is to actually get data from many different databases. So you can actually get large data sets from Materials Project, Citrine, or Materials Data Facility, and actually get a data frame or an Excel sheet with a whole bunch of data points in it. The other big thing that MapMiner does is this feature extraction problem that I talked about, which is turning these materials quantities like carbon diamond into a whole bunch of features like, hey, carbon is 4 coordinated, or carbon has a certain electronegativity, or the element carbon has a certain melting point, and to turn these numbers into things that the machine learning models can pick up on. MapMiner doesn't do the machine learning models itself. There's a lot of great libraries from the computer science community to do all of that stuff. So rather than trying to reinvent those, we just try to focus on the parts that are really specific to material science, which is getting materials data and turning materials quantities into numbers for the machine learning algorithms. MapMiner also does some visualization as well. One of the key things, though, is this feature extraction step. And what we've done is we've actually written over 50 now, I think, featurization classes that can generate thousands of potential descriptors based on material science quantities. So for example, if you have a crystal structure, one of the techniques that's been developed in the field is called an orbital field matrix, which will turn this into basically a vector of numbers. And there's an entire paper dedicated to describing this technique. Normally, you can find an implementation of it, but we've actually implemented it in MapMiner, and so now you can just call a code that looks something like this, and you will actually be able to get the numbers for an orbital field matrix. There's an entire paper that turns a site in a crystal structure to a fingerprint called an Agni fingerprint. And again, we've implemented that in a consistent interface so that you can just try all these different techniques that have been reported in the literature and see which ones are the best for your machine learning problem. I want to talk about one featurization thing that we've been developing in our group, which is this crystal site fingerprint, as well as a site statistics fingerprint. And these are ways that we'd like to turn a crystal structure into a vector of numbers for machine learning and for other applications as well. So the crystal structure, so the arrangement of atoms in a cell, is basically one of the core things that's important for material science and that machine learning algorithms should know about. But there's no standard way to turn a crystal structure into a vector of numbers. So one thing we did is we developed a technique that it starts with a site fingerprint that takes each site in the crystal structure and tells you how similar it is to different types of local environments, like a tetrahedron, an octahedron, or even an 8-coordinated cube. And it will actually turn the site into a vector that says, hey, I'm like 90% tetrahedron, maybe 10% octahedron for this particular site. So you have a vector for every single site inside your structure. And then what we can do is describe the structure as the average of the site fingerprints or even like standard deviations of the site fingerprint statistics. And that now your crystal structure is actually turned into a vector representation as well. So both sites and structures are basically vectors pointing in some multidimensional space. We spent a lot of time on these site fingerprints, and what we did is we developed something called order parameters. So here's what the tetrahedral order parameter looks like, and this is the central site you're trying to describe. And we want this order parameter to equal 1 if it's a perfect tetrahedron and go far away from 1 as you start to distort this tetrahedron. So this is a parameter that can tell you for any crystal structure or any site in a crystal structure, how close am I to tetrahedron, with 1 being a perfect match and going away from 1 being a non-perfect match. And we've developed these order parameters for many, many different types of local environments. So if you have local environments in your crystal structure and you want to know, is it like a perfect octahedron? Is it half octahedron, half square planar? Is it a distorted octahedron? These order parameters can describe how well a single site in your structure matches these different types of motifs. Some of the material science applications of this is, for example, defect and interstitial site finding, where you can actually make a grid inside of your crystal structure and look for empty spaces in the grid where you have a high value, for example, your tetrahedral order parameter, and that will tell you places in your structure where you can insert a tetrahedral site, for example, with a really good quality tetrahedron, for example, similar with octahedral sites. You can also use these order parameters to characterize diffusion paths. So if you have magnesium diffusing from a tetrahedral to an octahedral back to a tetrahedral site, you can use these order parameters to describe how the coordination of magnesium changes from tetrahedral down back up to tetrahedral and octahedral spiking here. So one thing we did with this is that we actually released a tool on this materials project website where you could take these structure fingerprints, which are the collection of site fingerprints, and get similar materials. So this is something that's typically hard to do. But you could take a target material like tungsten and say, show me more complex versions of this crystal structure. So this is the same pattern of atoms, for example, but with different types of combinations of elements in it. So you can get more and more complex versions of it. And you could even start with a really complex crystal structure and show me what's the more simple prototype of it. We've also started using these structure fingerprints to draw crystal structure families based on local environment similarity. So these are a bunch of, for example, mineral crystal structures. And what we've done is we've taken the structure fingerprints for every single one of these and used a hierarchical clustering technique to show me which structures are the most related to one another and drawing crystal structure families of related types of structures. So for example, spinel and olivine, these are, okay, let's start up here. So here's an FCC crystal structure, and here's what the structure fingerprint looks like. And these three components of the structure fingerprint are high. And these correspond to the FCC structure having coordination number 12 and kind of a cube octahedral type of environment. And both FCC and HCP are very similar in local environments because they're both close packed structures, and they're really close to one another in this dendrogram as well. These diamonds, barium aluminate, and chrysobolite and quartz structures, these are all very tetrahedral compounds, and they're all clustered together as well. Spinel and olivine are known to be really similar to one another, and they actually have lots of phase transitions between the two, and they're also clustered together as well on this diagram. So you can start to redraw these crystal structure families, which is typically done using global symmetry features, but by using local features, and we're starting to get some interesting results coming out of that. The last thing I want to mention with MapMiner is that we're developing a tool called MapBench. And this is basically a black box machine learning system where you can upload any data set of materials. You can say, you know, I've done some experiments and I have some formulas and I have some bulk modulus values. And I just want a machine learning model that relates these two things together. What we will do is we will actually automatically build a machine learning model. So we'll do all that featureization. We'll select which features are working the best for your data. And then we'll use some auto machine learning tools like TPOT, XGBoost for getting faster random forests, and trying lots of different types of machine learning models and seeing which ones are working the best on the data set and giving you a final model out. So typically, this whole process is done by a researcher manually, but just like with this high throughput DFT, where we took something that was manually done and made it really automatic, we're doing that same thing now for machine learning and saying, hey, a lot of the stuff that people are doing to make machine learning models could just be automated. Oops. So here are some results from that. These are two different problems that were presented in the literature, predicting formation energies of bulk materials based only on the composition and crystal structure, and also predicting band gaps based only on the composition of the material. And the bars, basically, higher means better. So we basically normalized the error of these two different problems so that higher meant better performance. And this is like a hand-tuned literature model where they wrote an entire paper about the machine learning model. And then the blue is what we get with our auto machine learning algorithm. And so this is just two different problems to show that we can get pretty close to literature values just using an automatic technique. But we're testing this on about a dozen different problems. And so far, it's been showing that we can get really, really close to literature models just with a completely automatic algorithm. Okay, so if you're interested in MapMiner, just like with Atomate, we have lots of ways for you to learn more about it. So we do have a paper about it. We also have documentation, and in this case, the documentation has maybe a dozen different Jupyter notebooks as well that really walk you through a whole bunch of different examples. And again, we have a support list that you can just email your questions to and get free support. Okay, so the last topic I want to talk about in the last 5 minutes or so is a new project we're doing with text mining and natural language processing. So there's a lot of data in materials that's just in text, in journal articles, and not really in a structured form like Materials Project database. And what we've been trying to do is to actually make sense of some of this data. And what we did is to actually collect over now 3.5 million different abstracts of material science articles. So going through all the different material science journals, collecting the abstracts, and putting them in a database. And then we wrote basically a machine learning system that will actually start labeling things like what material was mentioned in this abstract, what sorts of synthesis techniques were used, what sorts of properties were measured in the abstract, and just compiling all of that into a database as well. So now we're actually processing millions and millions of journal articles and trying to figure out what's going on in these different journal articles. One of the things that we're doing with this data is we're actually building a revised material search engine. So for example, if you look at this bismuth ferrite material, which is discovered in around 2003 to be a really good multiferroic material, you can kind of see that interest in this material really spiked right around when it was found to be a multiferroic. The types of properties that are studied are typically things like magnetization or ferroelectric, ferromagnetic. The types of applications of this material are heterostructures. In fact, it's also a photocatalyst, which a lot of people in this community typically don't focus on. The types of phases that it's known for is like perovskite and orthorhombic and tetragonal. These are the types of synthesis methods that it's typically made with, and these are the characterization techniques that are often applied. And you can click any of these links and it will show you which papers are relevant to that topic on this material. Similarly, we can kind of invert the problem and say, hey, I'm looking for every material that's been studied as a thermoelectric, but doesn't have lead or bismuth in it. What are all the things that have been studied for thermoelectrics that have that criteria? And it will actually list all the different materials that have been, like all the different chemical compositions, and rank them by how relevant they are, how often they've been talked about for this thing. So if you're just doing a literature search and I want to say, I want to find all the thermoelectrics that are Zintal-based phases. I'm writing a review on Zintal-based thermoelectrics. You can just say, show me all the chemical compositions that have the phase label Zintal, and it will just give you a list of everything that's been studied for that application. Okay, so what about finding new materials rather than just searching for existing studies? We actually came up with a way to actually try to predict new materials using this text mining. What we first do is we start with all the different chemical compositions in our text library, and we have a way to turn these chemical compositions into to vectors. And then what we actually do is we identify which compositions have a high correlation to the word thermoelectric. So there's a vector for the chemical composition, there's a vector for the word thermoelectric, and we see whether these vectors are pointing in the same direction or not, or whether they're pointing in opposite directions. And then what we do is, for all the things that actually really have a high correlation to this word thermoelectric, we filter out the ones that explicitly have the word thermoelectric in it to make sure that we are only including studies for compositions that have never been studied as thermoelectrics before. Okay, so one verification that this works is we actually compare text mining predictions of compositions with high correlation to thermoelectrics with independent computations. So I mentioned that big database of computations we did before of thermoelectric properties. So here's a distribution of computed power factors for, I think, about 20,000 different materials. They peak around, around 10 or something like that. And then if you just focus on the known thermoelectric materials, the power factors are, of course, higher because these are things that have been studied as thermoelectric, so they have higher computational power factors. If you look at the first 10 predictions that were made just from the text mining without any knowledge of the computations, they kind of fall in like the 99th percentile, all above like the 50th percentile for sure. And they all are really, really promising from the computations. So what this is showing is that the text mining is actually predicting things that the computations would independently confirm as being good thermoelectrics. We did one more test, which is we actually looked at, what if you just, okay, well, you can still read it. So what if we just looked at articles that were published until the year 2000, and then we used our system to train what would be good thermoelectrics based on information only until the year 2000? What fraction of those materials would have actually been studied as thermoelectrics later on? So if we went back in a time machine to the year 2000, did this study, would we have predicted actual thermoelectric materials? And from the top 10 predictions, about 80% of the things that we would predict as good thermoelectrics in the year, using data from the year until the year 2000, would have been studied in the subsequent 18 years or so. So it's actually showing that many times, years in advance of the actual study of a material as a thermoelectric, we can actually predict that, hey, these are the materials that are going to be studied in the near future by researchers. So what we're doing now is we're taking our data up until the year 2018, all these new thermoelectric predictions that no one has made yet because we're still in 2018, and trying to see whether we can make some of these things and show whether they're good thermoelectric materials. One last thing that you might be interested in is, well, how is this like weird text mining thing working and actually predicting new materials? Actually, it's very similar to how experimentalists might do the same thing. So here, for example, 3 different materials that were tested, that were predicted to be interesting for thermoelectrics from this text mining system. And we looked at, what are the key words that are really causing this to have a high correlation to the word thermoelectric. Lithium, copper, and timonite is because it's mentioned as a Heusler compound in some studies, and there's a ton of thermoelectric materials that are known to be Heusler compounds as well. So it's similar to how an experimentalist might say, hey, I'm interested in Heusler thermoelectrics, here's a Heusler that hasn't been studied before. The text mining is kind of doing that same thing automatically. Similarly, it might say that, hey, there's a big overlap between thermoelectric materials and photovoltaic materials. I mean, both applications involve semiconductors that need to be doped and have like an intermediate band gap, for example. And so here's the material that's been measured a lot for electrical properties in photovoltaics, but has never been tested as a thermoelectric. So it's making these cross correlations between fields and trying to figure out what might be new in this topic. Okay, so just in conclusion, there's many new methods that are being developed that basically combine theory and computation and machine learning that try to accelerate the rate at which we can find new materials for different types of applications. The rate of change is definitely accelerating in the computational field. So, quantum mechanics in the 20s, DFT in the 60s, high throughput DFT in the 2000s, materials databases, and machine learning all coming in the 2010s, and the 2010s are not even over yet. So more and more new things are coming. People are coming with new ideas, but we certainly need more effort and more people working on these topics. So with that, I'll maybe leave this slide up, which lists many of the people that are involved in these efforts, although it leaves out many more people than it lists. Mention funding from DOE and Toyota, and computing from the Nurse Computing Center. Did you say why VASP? Yes. Oh yeah, so the main reason we use VASP is because the pseudo-potentials are like really well tested in VASP. And so people basically trust VASP results. In terms of speed, I would say VASP still is faster than the other codes out there. But Quantum Espresso, I think, is getting kind of close. But like Abinit, for example, I think is significantly slower than VASP. You need like much more computer time to do the same thing. But yeah, there's many reasons, but I would say the quality of the pseudo-potentials and the trust of the pseudo-potentials is the main reason.
So when you showed your results for the thermoelectrics, right?
Yeah.
You showed that you had a model that was way better than Bootstrap.
Yeah.
Is there like a scattering mechanism that Bootstrap isn't considering, or why is that?
Yeah, so Bootstrap actually isn't considering scattering at all. It just has a constant relaxation time approximation to the Boltzmann equation. And you have to enter what that relaxation time is. So it doesn't model scattering to tell you what the relaxation time should be. This other model that I showed called AMSET is actually using things like the bulk modulus and deformation potential to kind of somewhat model different scattering processes and give you an idea of what this relaxation time should be.
It's not doing anything to model like a full scattering.
No, it's not like a full electron-phonon coupling calculation, for example, which is much, much more expensive and actually gives you like the explicit scattering. So.